right, so we had started this whole vector portion of chapter 6. We started off with geometric vectors, and it was kind of cool to see how this all plays out geometrically, but we're looking for a shorter way to combine vectors together. And so this is day 2 of vectors. You've done all the notation and the vocabulary and kind of the basics of vectors. Now it's time to dig in and actually figure out how to do these geometric vectors, but to do them more algebraically. And then we're also going to look at some applications of vectors. All right, we're going to start off and do a recap from the previous part of the 6.6 part 1 here. And we're going to start with this directed line segment that I've given you. So LM, when you use 2 points here, and L is the initial, M is the terminal. I've given you the 2-ordered pair. This is what we would call a directed line segment, but I want you to take that directed line segment and put it in component form. So again, I'll squeeze this in over here, from our previous class, I know, okay, so -5 up 3, I'm kind of just eyeballing this, and then over 2 up 6, so something like this. This is this directed line segment right now, where this is L and this is M. But what I want to do is I want to put it in component form. So recall that component form takes that vector and sticks it down at the origin. So it's still going to have the same direction and the same magnitude, but it's going to come out of the origin. And ultimately, I'm looking for this terminal point. To find that, we're just looking at what happened horizontally with the vector. And so I can look at this. It went from a -5 to a 2 horizontally. So to find that change, you're going to take your x2 minus your x1. So this is going to be vector P in component form. And the order you do this is important. You have to take the terminal minus the initial. So 2 minus -5. And then you do the same thing with the vertical components. It's going to be a 6 minus 3. Remember that the order that you do that subtraction is important because it's going to dictate the direction your vector goes. Change those. So that ends up being a 7, 3 for the vector in component form. Now I'm going to continue to use this vector P. So the next question says, can you find the magnitude? All right. Notation looks like this, where you put the bars around it. And the magnitude is, recall that this comes kind of like from the Pythagorean theorem idea. You're going to end up taking the horizontal component squared plus the vertical component squared. So that's 49 plus 9. That's going to end up being the square root of 58. Now I could reduce it. It doesn't happen to reduce. So I'm going to leave it. Although I do want to have just kind of an inkling of how long that is. Can you just, without a calculator, estimate, ballpark, what do you think the square root of 58 is? Okay, hopefully you're saying somewhere around like a 7.6 or something like that. All right, so that's how long it is. Now, the next thing they want is they want to find the unit vector in the direction of vector P. So I still want it to go this same direction, but instead of it being this long, this 7.6 unit long, I really just want this to be a tiny little unit vector in that same direction, but it's only going to be, remember, a unit vector has a magnitude of 1. So to figure out what that vector would be, I'm still going to take vector P, and I'm going to use vector P, but I'm going to reduce it by this square root of 58. Now this is now a unit vector, so I'm going to use a U instead of a P, and the magnitude is going to change, so I can't continue to call it P because it's going to change on us. And what we did is we took the horizontal component, and then we divide by whatever we found the magnitude. And we were in luck because they let us keep it in this format. We did not have to rationalize. So this would be the vector that's in the same direction, but is only 1 unit long. We call it a unit vector. All right, the reason for using the unit vector is kind of more for this next part. It says find vector W in the direction of P. So it's still this same direction, such that its magnitude is 8. Oh, so now we want it to be longer. We want it to come out here somewhere. Well, it's a little bit tricky with the initial vector because the initial vector was like a square root of 58. But if you consider the unit vector, now that's going to be easier to work with. That is only 1 unit, and I want to find the vector that's 8 units. So all you have to do is take your unit vector times 8. It's got a new magnitude, a new length to it. So they got a new name. It's now vector W. So I'm going to go vector W, which really what I'm finding is 8u. All right, so 8 times the unit vector. You're just going to multiply it times 8 over 1, which means it's only going to affect the numerators. The square root of 58 is going to stay. Now for the vertical component, we are going to take the numerator again times 8, so that's going to become a 24 over the square root of 58. That is, if I were to go find the magnitude of that, it would end up having a magnitude of 8. The last thing is to write this vector W that I just found, to write it as the linear combination of the standard unit vectors. That is so crazy wordy, but it's kind of fun to say if you say it fast after a while. So to write it with the linear combination of the standard unit vectors, all we're doing here is the linear combination means you're going to be adding or subtracting, and the standard unit vectors, remember, are vectors I and j. So I'm just going to take this same vector here, the same numbers, but just write it differently. So it would look like this: 56 over square root of 58, vector I, and then it would be a plus sign. It can be a minus if this next term was negative, but then you write 24 over square root of 58, j. Do not put a comma. Don't put the pointy brackets, none of that. It's just a plus sign with your I and j. All right, that's what we did previously. Now let's jump in and do a little bit more of what would be considered geometric vectors. So if we go back to the unit circle and think through that, remember we call it a unit circle because the radius is 1 unit. Okay, if you think about that and you draw in a radius right here, if this length is 1 unit, it really creates a unit vector because a unit vector has a length of a magnitude of 1. Now, if I'm trying to write this unit vector in component form, I would need to know its horizontal and vertical component at this terminal point. And just thinking back of how we do SOHCAHTOA and unit circle stuff, this x value would be, well, heck, let's just go back to this. If I was looking at the theta, if I did cosine of theta, that should equal adjacent, which is this length, which is x, over hypotenuse, but hypotenuse is 1, so it looks like this. And so the x value is really just cosine theta. So that's what I wrote here. The x value is really just cosine theta. And the y value is just going to be the sine theta. Now, what's going to happen as your magnitude grows, though? So this is what it would be. If I wrote the unit vector in component form, it would just be cosine theta, sine theta. But if it's not really a unit vector and it extends farther out here and the magnitude grows, well, that's going to make your x and your y grow also. And so now your cosine theta is going to be x over, and it's not going to be over 1 anymore because this is no longer a magnitude of 1. It's longer. So whatever that magnitude of that vector is would now be your denominator. And so if you think about it, now it was a u, but if I make it longer, it's not a unit vector. It would look like this now. And so that's what I would put it over, the magnitude of that vector. So now what the x value ends up being is if I take both sides times that denominator, now your x value is going to be your magnitude times your cosine theta. So magnitude doesn't always have to be 1. And what that's leading us to here is a realization that your x value in your component form is always going to be your magnitude times your cosine theta. And that would work even if it was a unit vector, but it always works regardless of how long your vector is. So I've got an important slide here in your notes to kind of show that. So what we're doing here is we're kind of looking at a geometric vector, and to try to write that in component form, well, all you really have to do to get it into component form is take your magnitude times cosine theta. And the magnitude and the theta are the two things that we are given when we deal with geometric vectors. So this little formula right here to convert a geometric vector into component form, we're going to be using that a bunch. So let's just practice one here. Find the component form of this geometric vector 5 centimeters at 120. So that's going to be some vector like up here, where your angle is 120, it's 5 centimeters long. What I'm looking to do is write it in component form. So then I would say this vector would be the magnitude times the cosine of theta, and then the vertical component is magnitude sine theta. Now I happen to give us one that's right on the unit circle. So the cosine of 120 is negative 1/2, and the sine of 120 is root 3 over 2. But those each have to get multiplied by that magnitude. So final answer in component form would be 5 times negative 1/2, so I'd call it negative 5/2. The vertical would be 5 root 3 over 2. And then without digging into what those are as decimals and stuff, but it does go left 5/2, up 5 root 3 over 2. And so it would land in that same spot. It's just written differently. Okay, so now let's try going the other direction. What if it's already in component form? And I want to turn it back into a geometric vector. So I'm thinking I need to know magnitude and theta. Well, we've got a way to do that too. So let's start off. If the vector looks like this in component form, actually the first thing I would do is look at what the magnitude is, and we can do that real easily with our formula for magnitude. So it would be the square root of 3 squared plus negative 2 squared. So that becomes 9 plus 4. So our magnitude is going to be the square root of 13. Now, the next thing I have to do is find theta. So I'm going to very quickly kind of go through this. I'm going to try to have some of the math in my calculator already done to kind of hurry us along. But ultimately, whatever this is right here, it should equal 3. And whatever this is, it should equal negative 2. So I should be able to take the magnitude, which is square root of 13, times the cosine of theta, which I do not know what theta is yet. That's what I'm looking for. But that should end up equaling 3. Or I could also do this. Square root of 13 times the sine of theta should equal a negative 2. If I'm solving for theta, I would first divide by that magnitude. So it's 3 over root 13. If I was doing the sine, it'd be sine theta equals negative 2 over root 13. And what you're going to do then is you're going to do the inverse. So it's the because you're looking for theta, inverse of 3 over root 13 should get me my theta value. I could do inverse sine of negative 2 over root 13, and that should get me theta. When I type that in my calculator, I find out here that theta is 33.69. But when I put it in on this other one, I got it to be a negative 33.69. Now, here's the deal. I did it on both scenarios, but I shouldn't be doing on both of those. Theta is theta. I should not have to do it twice. I should have gotten the same answer both times to find out what theta is. So one of those is correct and one isn't. Do you know which one would be correct and why it should be correct? All right, hopefully you're noticing that this original was a quadrant 2 vector. No, it wasn't. It was a quadrant 4 vector. So when I look at these two angles, this one is quadrant 4. This is not. I should not have ever been using cosine, because when you do inverse cosine, remember that you're going to always pull answers from first two quadrants. But if you do inverse sine, you'll get answers in these two quadrants. So I like this second answer. So next time I'm going to pay attention to that quadrant first, and I'm only going to do that once. Now, one other thing, though, I don't really love the negative angle. When we were doing this on your geometric vector homework, I never gave you a negative angle for your vector. So probably what we would want to do here, and we've done this different times where you add pi. Sometimes you add 2 pi. What would we do here and why? Well, first of all, it's not going to be pi or 2 pi because I'm in degree mode. But think about what I'm trying to accomplish here. This is in the right spot. This angle would fall right where the vector is. So it's not like I'm trying to get across over to the other quadrant where I had to add pi to get it in the proper quadrant. That's not what's going on. I still want to be fourth quadrant. I just want it to be positive. So I'm just going to do a quickie plus 360 to get it into quadrant 4, but as a positive angle. So when I do that, 360 plus the 33, actually plus a negative, actually it's going to be 360 minus that, is going to get me, oops, 326. So here's my official answer, 326.31. Okay, and kind of running out of room here. Here's my, okay, so that was my finding the directional angle, but really my goal here was to convert this to a geometric vector. And so you would say that vector v is square root of 13. And when we were doing geometric vectors, we were making it be like in centimeters. So you'd have a label there, square root of 13 centimeters at 326.31 degrees. So when we were doing, when I was reading off answers for your geometric vector worksheet, I actually had gone and done all of them algebraically like this and got actual true answers. And so I wasn't just trusting my drawings. It really was like a very accurate answer on that. Let's try one more of these, but I want you to take a look at this one. And do you recognize why this one might get a little trickier? Right here, when you look at this vector, this is going to end up being in quadrant 3. And quadrant 3, either inverse sine nor inverse cosine get me a quadrant 3 angle. So you can get to that angle multiple ways. I typically will just go ahead and use sine. There's a reason that I use sine. I think it just plays out and it looks, it's pretty straightforward. It's not going to get me the right answer, but I can get to the right answer pretty quickly. So I'm going to not do the cosine version. I'm going to do the sine version, and then I'll show you how to tweak it. First thing I'm going to need, though, is the magnitude. So you're going to be doing square root of 7 squared plus negative 1 squared. So that's going to end up being a square root of 50. It could be written as 5 root 2. I'm going to use whichever version is easier to type in my calculator at the time, which is probably going to be the square root of 50. But my final answer I will write in a reduced format. All right, so here's what I'm going to do. I'm going to go ahead and use the sine version. And I know that this right here should end up equaling negative 1. So I'm going to do the square root of 50 sine theta should end up equaling negative 1. So in my calculator, and you do this enough times, you're going to be able to do this more quickly. The last time I wrote it all out, ultimately I'm going to divide by root 50, and I'm going to have to do inverse sine. So I'm just typing in my calculator, second sine of negative 1 divided by root 50. Okay, and I got theta to be negative 8.1. Now think about where that is. Negative 8.1 would be like right here. That is not the proper quadrant. What your calculator is doing is it's giving you the angle that has the same sine value as this given angle. So the sine value is your y value. So the other place that you would have that same sine value would be right here. They're both down the same amount here. So this angle is our 8.1, but it's negative. But that also means with all the symmetry, this is a little 8.1 degree angle also. So what I like about this is it's pretty easy to visualize, oh, well, if I want the angle, ultimately I want this angle right here. Well, all that is 180 plus that little gap angle we found. So that's just 180 plus the 8.1. So this right here is what I would do. To get that angle, I'm just going to take 180 plus the 8.1, which I don't even need my calculator for. I'm just going to write it. I'm always just going to add it to 180. So theta that I really want is going to be 188.1. Now, if you're trying to use full values, and you probably should, then you could just kind of go back and add that in. But be careful, because in your calculator, it's going to be sitting there as a negative. And ultimately, we're looking at it like it's a little positive 8.1 degree angle that we're adding to that. So you might have to manipulate your signs a little bit. All right. So what I've done there is I have found the direction and magnitude of vector v. So vector v would be 5 root 2, and if we're just pretending centimeters or whatever your units would be, at 188.1 degrees. So now what I want to do is I want to do one more, because the whole point of us doing this was to be able to do your geometric vector homework without drawing this all out, and do it like I did it, where I did it all algebraically. So I'm just grabbing a problem from your homework on geometric vectors. Number 2 was just take vector b plus vector e. So what I did, if you'll recall in this homework, is there were 5 vectors that we used over and over. So I went and converted all of them into component form. So to convert b into component form, remember that it's going to be magnitude times cosine theta for your horizontal component, and then it's magnitude sine theta for your vertical component. And, oh, sorry, I don't even know why I was writing 0 or theta's there. I actually know theta, it's actually 0. So cosine 0, which is going to be nice, and then 1.5 sine 0. Oh, I do those thetas so often, my zeros sometimes turn into thetas. Okie doke. Oh, struggling there. Okay, so the cosine at 0 is 1, whereas the sine at 0 is 0. So vector b in component form is going to be 1.5, comma 0. All right. Now I want you to pause the video, and I want you to do the same thing with vector E. I want you to figure out what vector E is in component form. All right, go ahead, press pause, go do the math, come back to me. All right, so hopefully you got the same thing that I did for vector E there. So you can see that it's a second quadrant. You're going left and up, which sort of matches the vector that they're showing here. It'd be left and up. Okay, end up quadrant 2. But really, I don't even care so much about that, because what I'm looking for is my resultant. So the resultant I'm looking for would be vector E plus vector E. And all I'm doing is adding their horizontal components and adding their vertical components. So I'm going to take that, and I'm going to go grab full values, and I'm going to add the horizontal components together, and I end up with negative 0.77. And then when I add the vertical components, it's just going to end up that 1.06. Now, here's the deal, though. That's what the resultant would be, but that's not how you made your answer. Your answer looked like in geometric vector format, and so I have to do the same thing. This is great for my resultant if I wanted it in component form, but I want to know the magnitude and the theta for it, the magnitude and the direction. So first thing I'm going to do is I'm taking those numbers, and I'm going to run them through my magnitude formula. So I'm going to have, kind of running out of room. I'm going to change colors in case this gets a little cluttery. So the magnitude, remember, is going to be the square root of, be careful with that negative guy right there. Make sure that gets in parentheses, plus the 1.06 squared. But I'm going to go ahead and use full values as I do it. Then after you've square rooted it, you should get 1.3. And I actually remember that from when we did it. It ends up being a 1.3. And that would be centimeters. Now, the next thing you have to do is you have to find the theta. What is the direction angle of the resultant? And so when I look at this, notice that this is a second quadrant. So since it is quadrant 2, that should be dictating which I use, whether it's sine or cosine. And quadrant 2 would be cosine. So magnitude, cosine theta should get me my horizontal component, the negative 0.77. So using full values, I'm going to take and do inverse cosine. And I got 136.5 degrees. All right, so then that would be my resultant. This would be the direction and the magnitude of that resultant. And then that's what I told you the answer for number 2 was. All right, so that takes us kind of to a little more challenging problem. That's where we're headed here. And I love this kind of problem because it ties in so many different things that we have done. And maybe that makes me nerdy, but I just embrace my nerdiness. So we've got here angles and bearings and different ways of measuring angles. And we've talked a little bit about this, but I have even a new way of measuring angles. So let's go through all the different types because you've got to recognize what you're looking at and what you need and how you edit it or adapt it. So a direction angle. This is a math angle. This is what we do or what we use to complete math on it. So this is the angle formed by the vector and the positive x-axis. So this is just your typical unit circle protractor. This is your math angle. So I threw one up here. I called it's 160 degrees. Okie doke. Now, we've also dealt with compass headings, where you're basing it off whether you're north or south. And so this one here, this example would be based, it's a northwest, you're headed northwest, but the way we read it is it's 70 degrees west of north. So this right here is due north, and I am 70 degrees west of that. Okay, so these are all going to be, you can see all three of my vectors are the same vector. It's just that I would be representing them either as a 160 or maybe a 70 written this way, or the third one here. Another way to do bearings is by looking at the angle that is formed from due north, always north. So now we're ditching the idea that it could be from the south line. It's always going to be due north and the line of travel. And you're going to measure it clockwise, which is backwards from how we measure on the unit circle. We measure counterclockwise. So this particular angle is actually going to be an angle that starts due north and wraps all the way around clockwise to hit the vector. And we got to see what that angle would be. Okay, so there's different ways of doing that. We've already acknowledged that this little gap angle here is a 70. And so if that's 70, then this little gap angle would have to be a 20. So there's different ways that you might think through this. So now knowing that that's a 70 and that's a 20, I'm looking for what this angle would be. So Couple ways. You could say that it is 270 plus another 20. So that would be a 290-degree bearing. We use that word, we actually write the word bearing to indicate that's how we are measuring that. All right. Another way you might have thought through it is, oh, if this little gap angle here was 70 degrees, then what you are is you are 70 degrees shy of going all the way around. So I could do 360 minus 70, and I would get 290 that way also. Either way works. Let's go ahead and let's practice that a little bit so that this is just the baby part of a bigger problem. So let's go ahead and practice it so that we can be quick with it. So I'm going to do a couple things. I'm going to give you a direction angle, and I want you to turn it into a bearing. I'm going to do one, and then you're going to do one. I'm going to go ahead and put all my axes in here so I can change colors here. All right, so now a direction angle, this is our math angle, and we're going with a 200 degrees. So I'm thinking of just like unit circle, 200 degrees is somewhere down here. There's my vector. That's the direction angle. Now, to look at that in terms of bearings, bearings are always based, you start due north and you go clockwise. So I'm looking for that angle right there. So in order to do that, I've got to sort of figure out what some of these gap angles are. So right here, I went 180 plus 20 more. So that little piece right there, that little gap angle would be 20. But you might also then realize, oh, well, then down here, that would be 70 because it's got to make a 90-degree angle there. So whether you use the 20 or the 70 doesn't matter. But ultimately, my blue angle, my bearing, would be 180 plus another 70. Or it could be 270 minus the 20 because I didn't quite make it to 270. Either way, I'm going to land at a bearing of 250 degrees. Okay, so now go ahead and, well, tell you what, I'm going to go, nope, I'm going to make you stop. Sorry. Go do that. Pause the video, you go do 70, and then come back and see if you got the right thing. So pause the video right now. Try it on your own. All right, so I got that to be a 20-degree bearing. And so that's just looking here. First quadrant would be a 70. That's what I think of in math terms. But if I come from due north, I'd have a 20-degree of tiny little bearing measurement there. Okay, so that 2070, I feel like we use that a lot. It is total accident that I end up with a bunch of problems here today that all were 2070s. That's, I don't know, must have been my lucky number that day. Okay, now I'm going to go the other direction. So now I'm going to give you bearings, and I want you to turn those into direction angles. So this one is a bearing of 320 degrees. So when you're drawing the bearing, you start due north and you start going this way. Well, there's 90, 180, 270. I'm up here somewhere. I'm at 320. Now, I feel again like it is helpful to know some gap angles. So when I went to 320, I couple ways to think of it. I would think of it as I was 40 degrees shy of making it all the way around. And if that's 40, then this over here would have to be 50. So that's how those would split. But now what I'm going to do is I'm going to turn that into my math angle, my direction angle, so I can go perform some math. So mathematically, I would be looking at this vector. I'm trying to get to this same vector, it goes right here. I'm just changing the color of it now. So it's red instead of blue, but it's still in the same spot. So I would go this direction. Okay, so for me, I would probably look at that as I went 90 plus another 40. So 90 and 40 ends up giving me a direction angle of 130. And I could go do some math with that 130-degree angle. Okay, take a moment to pause the video and you go do the 110-degree bearing and turn it into a mathematical or a direction angle. I told you for some reason 20 and 70 were my lucky numbers that day. So here's another example. I ended up accidentally with another 20 and 70. So 110 bearing, start due north and go 110 degrees this way. So this is 90, and I ended up going an extra 20. So I know this gap angle is 20. This little gap angle would be 70. So now if I want to try to do math, I've got to think unit circle. So to get to this same vector, I have to go this way to get there. And so for me, I would think I'm 20 degrees shy of making it all the way around. So there's my 340-degree direction angle. All right, hopefully that makes sense. Let's keep moving. Now, I just have one problem that we're going to do here, and I've given you 2 slides, but I'm going to try to sneak it in, and I'm going to scooch this over so I have a little bit of work room here on the side. You're going to go ahead and do it on the next slide, but this is the problem that I love because it ties so much together. So just as a reminder, this is the component form, how we write a component form of a vector. And by having it in component form, we can easily add, subtract, multiply vectors together. But oftentimes those vectors are given in geometric form. So here's what I have. I've got this airplane that it's flying on a compass heading. I'm trying to use all the different words that they use on your homework. I feel like the verbiage is sometimes confusing. So they say compass heading, but they mean it as a bearing of 340 degrees. And that plane is flying 325 miles per hour. So in this case, the magnitude is going to be representing the speed of the plane. So this is going to be a nice, really long vector, 325 miles per hour. Now you also have this wind vector that's blowing you off course a little bit, and it has a bearing of 320 degrees at 40 miles per hour. Okay, so first thing I'm going to do is get rid of those bearings because I can't do math with those. So I'm going to take my 340, and that basically is, if I were to sketch that out, I'll just go ahead and do it right here. 340 for a bearing would come all the way around here, and I would be 20 degrees shy of making it all the way around. So then mathematically speaking, if I'm coming this way, that'd be a 90 plus a 20. So I'm going to cross this off. I purposely cross it off. I will never use that number, and I'm going to use a 110 degree instead. All right, the wind vector is at 320. So if I were to go this way, instead of making it to 340, I would only make it to 320, which means going this direction, I would end up at 130 degrees. I'm going kind of fast through that because hopefully you can practice that enough. That's not where I want to spend our time. Now, I think it's very important to sketch this out so you have some idea of how this is going to play out. So think of how you did this with the geometric vector homework assignment. And on the next slide, I have a little graph for you to fill in. So what's happening here is my plane is headed at 110 degrees. So here's my plane. It's going at 110 degrees, pretty long vector, 325 miles per hour. And I'm going to graph this like tip to tail. So where that one ends, my next one begins. And so this doesn't have to be a perfect graph. I just want you to envision what's happening here. That my next one is at 130. So that's a little bit more, going a little bit more westward. But what's even more important is to recognize your magnitude is much smaller. So this is a little baby vector right here. That's your wind vector. I'm taking my plane, I'm adding the wind, and in the end, this right here is the resultant. And that is what I'm searching for, is that resultant. I want that resultant as a geometric vector. I want to know the magnitude and the direction because that's what they were giving me. That's how they would expect to have the answer back. But I'm going to have to get some conversion going to do that. One thing before we jump in, though, that I want you to recognize is, do you feel like the wind is helping that airplane move faster, or is it slowing it down? Well, if you look at your drawing, you can see that your resultant vector is longer than what the plane vector by itself was. So you should find that your answer ends up with your plane moving faster than what it was by itself. The wind is helping. Now, it's throwing it off course, but it is making the plane go faster. All right, so they have two things they want us to find. It says find the component form of the velocity of the airplane. And so when they say that, what they really mean is of the resultant. What is the plane actually doing? Not the plane by itself, but the plane and wind together. I want the component form of the resultant. After I have the component form, then they're going to want me to convert that to a speed and a direction. So then it's going to be more like a geometric vector. And I'm kind of picky on this, on how I want this set up. Here, I want it nice, clean, and neat. You can do a lot of work in your calculator. I don't need to see 1,000 decimals going. I just want to see you set this up. We're going to take our plane vector. You're doing this on the next slide. Plane vector. And I'm going to write what that would look like as a geometric vector. So its magnitude, the plane had a magnitude of 325. Cosine of the direction was 110. Remember, we're doing math. And then the vertical component would be 325 sine of 110. But what I'm doing, and you can see from my drawing, is that I'm going to add the wind vector to it. So I'm taking the plane vector plus the wind vector. So we're going to stack these just like this. And if I add the two vectors together, I'm going to end up with a resultant vector. So we stack them vertically, and it looks just like this. And this will be my answer to part A right here, where they want the component form of the vector, of the plane. So my wind vector only has a magnitude of 40, cosine of, and it has a direction of 130. 40 sine 130. Now, I don't need to know what you're getting for decimals on that. All I really want to know is the resultant. Now, the resultant, it's going to end up a decimal because these are not unit circle values. But I would just leave them as is and type it in exactly in your calculator. Now, here's what I would do to save some time. I'm going to take this horizontal component plus this horizontal component, and it's going to get me my resultant. And I am going to do this all in one shot, and it's going to be a shortcut. So I'm typing in my calculator, so are you. Here we go. 325 cosine 110, close the parenthesis, plus 40 cosine 130, close that parenthesis, press equals. And what I have is a horizontal component of negative 136.87. We'll go 2 decimal places. Now, the reason I do it all in one shot is because what I'm now going to do is I'm going to go grab it, and all I'm going to do is change out those cosines for sines. And that way, I don't have to retype everything in. I just feel like that's a little quickie shortcut for us. And I got 336.04. I think it's worth a quick glance. Does this look reasonable for our picture? Left 136, up 336. I like the quadrant at least, right? Now, this right here is the answer to part A. We found the component form of that resulting plane ride. Now, the next part for part B, we want to convert that to a geometric vector. We want to know what is the actual ground speed. So in other words, what's the magnitude? So I'm going to do magnitude of the resultant. And you should be using full values here. So I'm going to go, well, and so you really got to watch out for those negatives. So I'm going to do an open parenthesis and then go grab that negative 136 number and close that parenthesis and then square it. Because if you don't have it in parentheses, it won't keep track of that negative sign going positive. You can also just take that number times the -1 and make it be positive before you square it, whatever you got to do. All right. And so after I add those, square them, add them, square root it, I am at a magnitude of 362.85. And think about what magnitude means. Magnitude is a speed, so this would be miles per hour. All right, so this was your answer earlier. This is the part B answer, at least part of part B. And I like that answer because remember, we talked about how the resultant was longer and that the wind was helping that. So we should be going faster than 325. And we sure are. We're going faster than 325. The next thing I have to find, though, is the direction I'm going. By looking at my sketch, my plane was going 110, but the wind is blowing me a little bit off course. So I'm going to be a little bit past the 110 mark there. So let's see what we would get. All right. Looky what quadrant. We're quadrant 2. I feel like we've done this a lot. Quadrant 2. That means I'm going to be doing cosine. So I'm going to do magnitude cosine theta, which is what I'm looking for, should equal my horizontal component, negative 136.87. All right, I'm going to use full values as I go. I'm going to do second cosine, and I'm going to divide that 362 over. So it's going to end up second cosine of the negative 136 number divided by the 362 number. And I get theta to equal 112 degrees. All right, I like 112 degrees because it does feel like, all right, it was at 110, but my wind is blowing me off course. But your wind is also a tiny vector. So it also makes sense to me that it's not very far off from where it was originally. Now, if I'm going a long ways, even though that's a 2-degree difference, it's going to make a difference. All right, but I'm not quite done because if I report this 112 degrees to some pilot, they are going to be thinking 112 degrees. They're going to be thinking bearings and they're going to be going this way. And they're thinking that doesn't seem right. We have to answer back in bearings. So I have to take my 112 that I'm thinking is this direction, and I have to turn that into a bearing, which is going to go this direction. So I would probably go ahead and find out what this gap angle is. So I'm going to take my answer and subtract 90 from it. And I get a little gap angle up here of the 22.16. And now if if the gap angle right here, I didn't make it all the way around the unit or around the circle, around the one revolution. So I'm going to do 360 minus that 22 number. Okay, and then my answer is, for what direction my plane is going in bearings, I would have 337. So you can still write theta equals here. It's a different theta. I'm just going to label it 337.84. And then I just write, and that's degrees, and then I just write the word bearing after it to clarify that that's a bearing measurement. All right, that's the second part of part B. All right, now I slow played that and tried to be very specific on how you work through that. Hopefully we'll get a little faster with it. I'm not going to do another example. If you need to watch it again, go for it. I promise we're going to practice this several times because remember, I love this problem. We're going to do it a bunch. Oh, wait, one more thing. In this scenario, I knew what the plane was set to fly, and I knew what the wind was blowing me off, what the wind was blowing, and I was looking at what's my resultant. Sometimes they mix that up. For instance, what if you already knew what the resultant was? You knew where the plane was going, and you were looking for what's the wind blowing? All right, so here is, you can sneak this in on your second slide there or somewhere. What we're doing here is we're taking the resultant and we're saying it is the plane plus the wind. But you can rearrange that little equation. So you could say that the plane would really be, if I was or actually, what did I say? I said I was looking for the wind. If I'm looking for the wind, just rearrange that. And the wind would be the resultant minus the plane. Likewise, if you were looking for the plane, you could do resultant minus wind. You can rearrange that little scenario. What would look different is this part right here, and this. Instead of having vector P plus vector W, you might have one of these other ones. Now, it is important to notice that if you're going to do subtraction, your resultant should be on top. So this would be the resultant. You would put a minus, let's say the wind, and then down here, you would have your plane vector. And maybe that's what we're searching for. It will happen on your homework. So be careful with those. Sometimes we will be subtracting. Remember, non-negotiable right here is what I want to see for work. This right here. Nice, pretty, organized work. All right, thanks. See you later.